joint random matrix given by the following matrix. The entry here is 1 over square root n times sigma I over n, comma j over n times xij. So sigma I over n, sigma is like a variance for these standard normals. Schleich-Tanko proved that the moments of a Gaussian band matrix exist using analytic methods. So we know that moments of such things exist, and they were proved around 1996 by Schleich-Tanko. Till now, we have seen self-adjoint cases and talked about moments of such matrices. But what happens in self-adjoint cases? So, let's introduce the operators. And how to introduce the operators as the distribution limit of certain upper triangular random matrices with diagonal entries mu distributed, where mu is compactly supported and off diagonal being complex Gaussian. So I have to edit something here. These are on the lower, strictly lower diagonal part, we have IID normals. But on the diagonal part, we have mu distributed random variables. I should have put a square root n here because these things do not have this normalization square root n on the diagonal. That's a little something that I missed while typing. These operators exhibit nice properties such as having spectrum equals to the support of measure mu. These operators include quite less circular operators. For example, these circular operators can be found if you take all these diagonal entries to be distributed according, have measure on unit disk in complex plane. These operators exhibit interesting combinatorial properties. So I was reading through these combinatorial properties, and hence I came up with the work which I'm presenting. So for that, let's look at definitions. That has the subset of 0, 1 cross 0, 1 inside R2. Such a subset is called a pattern if the area measure of the boundary of S is equals to 0. For example, the star shape here, clearly its boundary has area measure 0. It has no area. For a pattern S, its approximating matrix X and S of size n is a random matrix whose entries are arranged according to the given pattern. So here we can try to explain the algorithm how we create this. It's not hard. Look at so if we want to create an approximating matrix of say size say size 8 by 8, then we create these 8 by 8 grids and put this whole shape inside this square, and then we look at the intersection of grids with the interior of the given shape. So if the shape, which is star shape here, intersects with the given subsquare here, we shade it yellow and fill it with an IID random variable. If it doesn't has any intersection with the given shape, interior of the given shape, that's important, then we put 0 there. So that's the algorithm. Importantly, we need to know that we care only about intersection of the interior. So if there was something, if boundary was there was boundary which was intersecting with say one of the blocks, then we will again put 0. So there should be some interior of the shape inside this sub block to make it. Okay. As an example, again, this is a square shape, and we have the following approximating matrix. So a few more definitions, more technical. A finite sequence in formal variables, x and x star, is called a configuration and is denoted by C x comma x star. For example, C x comma x star can be the following word: x, x star, x star, x, x, x star. These are just words. And given a configuration C x, x star and a matrix X, let x to the power c denote the evaluation of the configuration at capital X comma capital X star. For example, if c x x star is given by the falling bird, then capital X to the power c is equals to capital X star, x x x star. So here capital X star denotes the adjoint of the random matrix, or generally the matrix X, and we take the product of these matrices according to the given bird. Its start movement under the configuration C is defined by taking the expectation of normalized trace of x to the power c. So these are generalization of the movements that we know for self-adjoint operators, but since these are not self-adjoint, we need to know how x star and x star is. A function I from the set 1, discrete set 1 to up to m plus 1 to n is called a closed path if the function has same endpoints. We will use certain type of strictly paired paths called the polar constraint path to prove the main theorem. I will not get into the theory of paths, but so we have, once I mentioned the theorem, to prove the main theorem that we have worked on a theory of paths. We have created certain kinds of paths, and certain kinds of paths seems very useful, and the most useful were polar constraint paths. And counting these paths essentially gives us the movements. So that's how combinatorics is related to the free probability theory here. So as an example, these are paths are just discrete functions. So take this discrete function. So this path is an example of polar constraint path. Usually, one of their nice properties that they have something called wedge, and around the wedge they are symmetrically distributed if we join the endpoints and think of this path on a circle. But more generally speaking, these are essentially the generalization of non-crossing pairings, but they are somewhat less than them, but asymptotically they are almost equal to the number of the non-crossing pairings. So this is another way of looking at non-crossing pairings. So the main theorem here is that given a configuration C of length 2n and a pattern S, the limit as the size capital N goes to infinity, expectation of normalized trace of x and s to the power c is equals to 1 over n plus 1 factorial times integral over n plus 1 dimensional cube of the function f sc n plus 1 dx. It's a in simple words, what it says is that on the left-hand side we have the movement of the pattern matrix x and s. X and s here represents the pattern matrix, and what this theorem says is that the movements of pattern matrix vertically, and they go to integral of a combinatorially defined function, which is given here. So it's averaging certain function, which is defined in combinatorially. So this function is called the path counting function and is defined combinatorially. It counts the number of polar constraint paths passing to the points x1, x2 up to xn plus 1. Again, since I have not defined what polar constraint paths are, but essentially that's what this function does.
Integer valued.
F is integer valued. It is a counting function. It just counts the number of things.
Can you remind me of the entries of your pattern matrix? They're just IID.
Just IID, no assumptions. No assumptions. Just the movement should exist. All movements exist, and that's all. Okay. So this is what we have, and we can try to prove this or give a sketch of the proof. We can try to do is we can take expectation trace xn s raised to the power c and trace expanded. So expand the trace. So while expanding the trace, this is essentially sum over all products of random variables of the entries of this matrix. So we take products over entries of the matrix in a way such that the indices match. So that's trace expanding my random matrix here. Then what we can do is to consider only the part which is non-zero, because we are taking expectation here. So it kills a lot of the terms inside product terms, especially the terms which do not have any pairings. So there might be some terms which have just one random variable and none of its copies anywhere around. Those terms are cancelled. So we are looking at only the paired things. We call such things social paths. So all the functions from 1 to 2n, so all the paths which have at least pairing going on are social paths. So we have taken sum over them. And amongst those social paths, we now decompose the sum as sum over polar constraint paths and sum over all the remaining social paths, modulo the fact that we are not counting the paths which are identically zero when we take the expectation. So what we can do is that this part, expectation of the product term here tends to be always equals to 1 because the variance is 1. So, and there is exact strict pairing going on. So there is one more copy of this random variable somewhere inside, just one, exactly one. So it's a expectation of square of this term and taking such, and every random variable has this property, and expectation of square of certain term is just 1 because variance is 1. So we get 1 here. And on this side, this is a collection of product of movements of 13. So this side will be bounded by some integer capital M because the collection here is finite in some sense. So you can the maximum number of movements we can count here are, say, of size up to 2n. So there will be just at most 2n and some combinatorial combination of them movements. So that's why this whole term is bounded above, because this collection is finite by some positive number m. And the major result we had is that these paths have asymptotically goes to 0 when compared to capital N raised to the power n plus 1. So we get 0 here, and this part, after doing some calculations, we get that this is exactly equals to 1 over n plus 1 factorial integral over the n plus 1 dimensional unit cube of the path counting function. So we had an inequality here, but this actually is equality because this term is always. So if you take modulus here instead of just this, so this is absolutely bounded by this sum here, and this sum goes to 0. So this sum has to go to 0, asymptotic. That means this whole term is exactly equals to this integral here, and hence the theorem. That's a sketch of the proof. A few more we can look at is that in this machinery we have, so while proving we have certain, we want to look at the movements of certain kinds of random matrices, and we passed on to the machinery of paths, and then that's how we computed these movements. So this machinery of paths have certain nice properties. For example, this machinery tells us that only the second movement of underlying random variables contribute. That's what we have seen in previous slide in the sketch of the proof. Also, it tells us that asymptotic movements of the pattern random matrix consisting of complex random variables exist. So it doesn't matter if you fill the pattern random matrix with a real random variable or a complex random variable. At the end, you're going to get the same results. the asymptotic mixed moments of Q-independent random matrices exist. That also goes the similar way as one variable case. This is interesting that freeness is observed only in the case of fully filled square matrices. So what do I mean by freeness here? I mean, if we take the collection of all pattern matrices, then in that collection, only so the freeness property in the sense that if you take alternating product, so if of matrices is followed only when we take completely filled matrix, and no other matrix has this property. Even if we take a matrix following a certain pattern and take its copy, independent copy, these are not free either for any of the patterns other than fully filled square matrix. And this has to do something with the fact that L1 and L2 norms of functions are always different, other than the case when the function is constant. And in this case, the constant function is represented by a fully filled square matrix. And finally, as independent pattern matrices form a free circular family with amalgamation over diagonals. If we go to the operator valued case, these form a circular family, the limits of such pattern matrices.
Is that for a same pattern for each of the independent matrices, or you can change the pattern?
You can change the pattern. It's for collection of things, independent collection. What we can do in future is to extend the work to more general patterns having non-zero measure boundary. So this part is very interesting. The reason we were restricting to things with zero measure boundary was because there was no framework. There is no way I can try to coherently create a random matrix out of a given pattern, because we don't know what a random matrix for something which for a curve which might fill the whole space and still have zero measure might look like. We need to find restrictions. Obviously, not every subset of say 0, 1 cross 0, 1 will have a nice approximating matrix, but we will have to look at certain other restrictions more loose than what we have right now, which might be interesting. Which entries are not necessarily independent. For example, Toeplitz matrix. There has been some work which I tried to do, and if nothing else, that the work that we tried to do at least gives us the right kind of normalization. For example, if we take Toeplitz random matrix, then the normalization which we used throughout in this slides, 1 over capital N raised to the power n plus 1, that doesn't work. We get, but there is another normalization which actually works for such cases. And this was seen using this method. And we can determine the measure corresponding to the moments of self-adjoint product of pattern matrices. So you can take pattern matrix and take, say, its adjoint and multiply to itself, its self-adjoint, and this will have a movement sequence in general sense. And we would like to see what the measure corresponding to that movement sequence is. We would like to study the round measure of limiting operator and study the properties of the limiting operator inside a von Neumann algebra. So the last point is very interesting, and it's related to the second last point somehow, but still it's unclear how to go there. From Dykema's DT operator paper, it's clear that if we have certain patterns like triangular pattern, then the limiting operator actually lies in a finite von Neumann algebra, and its round measure is known, but we don't know what happens in general patterns that we have here. So that's all for the talk today. Thank you for listening.